Hi everyone, in this video we are going to finish Unit 2. We're going to go through some phase change information with heating curves and phase diagrams. This unit has a lot of vocab, so this is just a little bit more vocab and how to read a couple graphs. And then we're going to go through heat transfer, which is a quantitative equation that we'll do. And that's the heavy math of this unit, but it shouldn't be bad. So from your textbook reading, we know that phase changes occur all the time, and we just need to kind of know this chart. The two that I will point out that sometimes people goof up on is we can go from solid to gas actually in one step and just avoid that liquid phase. This is called sublimation. This typically happens with dry ice, which if you've ever seen a fog machine, that typically has dry ice in it, which is just solid carbon dioxide going to gaseous carbon dioxide. And then deposition, this is actually going to be gas to solid, and we'll see this in class one time. And this is specifically going to be, or it's even more rare, but again, we skip the liquid phase, and we'll see this with iodine. So iodine gas going to iodine solid. Iodine is one of our Brinkelhoff elements. And so that's actually a very cool process to see that we will see in class. So the question says, as you move to the right on the chart above, what is happening? So as we move to the right, our particles are becoming further apart from each other. And we would say that their intermolecular forces are decreasing. And then as we move to the left on the chart, we're going more towards the solid phase. And so we would say that our particles are moving closer together to each other. And when particles become closer to each other, their interparticle forces are increasing. Okay. Now, vaporization, which is specifically going to the gas phase, we have evaporation and then we have boiling. And so if we look at these two pictures, both of them get us into the gas phase. But when we have evaporation, we typically see this, let's say, if we have a cup of water, we let it sit out. And between one day to the next, we might notice that the water level has decreased. And this is because evaporation is specifically a surface level phase change. In evaporation, heat typically comes from above, and so the particles at the surface level are the ones that get warm enough to enter the gas phase. On the other hand, boiling, our heat comes from the bottom. And let me change this to heat source. And so our bubbles, we see bubbles with boiling because the bubbles form at the bottom. And because gases are less dense than liquids, they will eventually travel up to the surface. With evaporation, you may wonder why we don't see bubbles, and it's because the bubbles just form right on the surface and then leave. So we don't have any bubbles traveling through our liquid. Okay, heating curves, and I'm going to make a note here. Sometimes we get heating curves mixed up with other sorts of things, but heating curves are going to look like stair steps. And as a substance is heated, the temperature can change, but does not always change. And that's very weird to know that. So as a substance is heated, the temperature oftentimes will change, but it doesn't always change. What you need to know, and I have these throughout our notes packet, is if we're undergoing a phase change, the temperature actually does not change. Okay, this is for sure a test question. Okay. So we have a heating curve here, and from this section we have solid. From this section we have liquid, and in this last section we have gas. So what is happening between A and B? So either if we're going from A to B, our solid is absorbing heat. If we're going from B to A, notice how we have double-headed arrows, so we can go up or down the curve. Our solid is releasing heat. And here the temp is changing. Now, from B to C, we're in this section, we notice that it's flat, and so our slope here is 0. Well, our y value is temperature, so from B to C, we have no change in temperature. So we have two situations. We could be going from B to C, or we could be going from C to B. So if we're going from B to C, we're going from solid to liquid. And when we go from solid to liquid, this is called melting. On the flip side, if we're going from C to B, this is liquid to solid. And this is called freezing. Now, from C to D, we're now here. We are either heating our liquid or cooling our liquid. So I'm just going to copy this. Actually, I'm going to copy the whole box because the same thing is happening. We just got to change the letters in the state of matter. So we could be going from C to D. In that case, the liquid is absorbing heat. Or we could be going down the slope with D going to C, where our liquid is releasing heat. And notice the temperature is changing. Okay, now D to E, we have D going to E, or E going to D. And notice our slope is 0 at this section. Okay, so there's no change in the temperature. This makes a lot of sense to me. One, the slope is 0, but we just highlighted at the beginning of this page that when we undergo a phase change, which is what we're doing here, the temperature of our substance remains constant. Okay, and that's something most people just don't know. And so we could be going from D to E. D to E is going to be liquid to gas. We could call that boiling. We could call it evaporation. Just depends. We don't have enough information there to know where the heat's coming from. We could also go from gas to liquid, and that's called condensation. And then in E, we could be going from E to, I guess, F, let's say. I don't know what F is, but that would just be our gases absorbing heat. Or we could go from F to E, where our gas is cooling or releasing heat. and our temperature is changing. I'm going to add one more thing here, and I'm going to add it in red. So if you have a different color, I would add this just because it's going to make sense when we get to the last part of these notes. If the solid is absorbing heat, or our liquid or our gas, that's going to be a positive, what we call a positive Q value. Q is what we're going to use as our variable for heat when we get there later. Now, I'm going to use, let's see, I wanted like a light blue, but this will be fine. If we're releasing heat, we're still dealing with heat, so it's Q, but it's going to be negative, okay? It's going to be important. And then we'll get to this, but I think this is a great place to put it, and it's okay for something to show up twice in the notes. A positive Q, that means heat is going into your system, and we call that endothermic. And I just remember that heat goes into, and I know I spelled into wrong, but that's so you can help it match it up with endo. And then a negative Q is called exothermic. And this is heat exits your system. Okay, now we're going to skip this next page. I want to cover that in class, so we'll just skip page 15. The last thing we're going to look at in this set of notes, and then we'll move on to the very last set of notes, is called phase diagrams. This tells you, for a specific substance, what the pressure and temperature combination that you have, what state of matter you will have. So for example, let's say this is just carbon dioxide. Okay, so let's say this is phase diagram for carbon dioxide. And let's say that we have a temperature of 250 Kelvin, which we'll talk about Kelvin, but that's just what this is measured in. And we're at a pressure of 500 bar. Well, I'm going to find 250 Kelvin. I'm going to move it up to about 500 bar, and that combination would give us liquid carbon dioxide. If I change the pressure to 5,000 bar for the pressure, we would keep going, and 5,000 occurs right about there. We'd actually have solid carbon dioxide. Let's say we had a different situation, and we had, I don't know, 300 Kelvin and maybe 95 bar. We would get, or actually, hold on, let me change that to do a better example. Let's say we had 250 Kelvin and 10 bar. Well, 250 Kelvin, 10 bar is right about here, so we'd have gas phase. But let's say we increased it, and let's say it was to 30 bar. Now we're on the line, and when you're on the line, you have each phase present. Okay. So for example, here we would have both liquid and gas. They coexist. There is for every state of matter, or excuse me, for every substance, there's something called a triple point where all three phases exist in equilibrium. And that's kind of a cool thing to experience, but you probably experience a triple point for water frequently, because on Earth there's instances where we could have liquid water, solid water as ice, and even water vapor present. You will not be tested on supercritical fluids, but if you want to write a couple paragraphs and look them up on your own, supercritical fluids, send me a Schoology message with either your couple paragraphs or a document with your couple paragraphs, and I will give you bonus points. Okay, so you can do that on your own if you're interested. We're going to cover Notes 5. Notes 5 is the math of this unit. Now, before we get there, you may notice that we have on each set of notes our phase diagram. They always sort of look like this. And I call them slugs. And that's because for every single phase diagram, no matter what the substance, this part's solid, this part's liquid, and then this part's gas. So I remember solid, liquid, and then the underneath one, this one, is going to be our gas. So that's just a mnemonic that I use. Okay, so let's do our Notes 5. We're going to quantify our heat transfer with specific numbers, okay? So quantify means using numbers. And so instead of just saying something is hot or something is cold or something gains heat or something loses heat, that's all useful, but only to a certain extent. We want to put numbers to it because we could really take advantage of things when we have numbers. So, basic rule of the universe. Okay, this has never ever been broken. Heat always flows from the substance with the higher temperature to the substance with the lower temperature. That is just how heat exchange works. Now, the amount of heat that is transferred depends upon how much heat is available, the mass of the sample, and then the identity of the sample. The identity is specifically important because some substances conduct heat well. Those are typically metals. And then some do not. Heat is going to be the lowercase q as our symbol. And we've talked about how a positive q is going to be endothermic and a negative q is going to be exothermic. The units of heat that we're going to use in this unit are going to be joules, and that'll be a capital J. Now, when you take AP Chemistry or AP Physics or other classes, you may see calories, and kind of interesting, we have lowercase calories and we have capital calories. The calories that you see on nutrition labels are always a capital calorie. And so I believe, and I would have to look this up so I don't remember exactly, but I believe 1 capital calorie is equal to 4.184 joules. Okay? But just sort of interesting that the way we figure out the amount of calories in food is that we actually burn them and see how much heat they give off. The system is going to be the part of the universe being studied, and then the surroundings is everything else. If heat is absorbed, we know that Q is positive, and that's an endothermic process. And if heat is lost, Q is negative, and that's an exothermic process. The first law of thermodynamics says that the energy of the universe is constant, so energy cannot be created nor destroyed. So even though we might have energy exchange, the total energy of the universe is going to be the same. Do all substances absorb or release heat in the same way? Obviously not. Some substances hold on to heat well, while others do not. So the way a substance holds on to heat, we are going to use a specific variable, a capital C, and this is going to be called the specific heat capacity. And it's specifically a measurement of how many joules it takes to raise the temperature of that substance. So, if you think about substances that are very easy to heat up, I'm thinking about metals. Metals conduct heat very well. So metals have very low specific heat values. Whereas nonmetals have very high specific heat values. Calorimetry, which is something we will do in lab, is it's a technique that we use to measure the heat gained or lost during a chemical or physical change. And so our setup will look like this. I don't need you to understand it right now because when we do this in lab, it'll make sense. But we typically have styrofoam, which seems very not scientific for a lot of people, but styrofoam is a great insulator. Okay, now this equation is called Q equals MC delta T. Q is the amount of heat gained or lost by our system, and we're going to measure that in joules. M is our mass. We're going to measure that in grams. C is our heat capacity. We'll sometimes call that the specific heat. And that's in units of joules divided by grams degrees Celsius. So those units are very confusing at first, but they'll make sense. And then delta T, delta in science just means final minus initial. So this is going to be the change in temperature. So we're going to solve out these problems, but let me go through the general way to do this. We're going to write the equation we're going to use. Always write our equation. We get a point just for writing that equation. We're going to plug in the variables that we know with their units. We're going to do our algebra. Some of you will use many steps for your algebra. Some of you will not. Just depends on how you sort of do algebra. And then we're going to solve for our unknown variable with correct units. These formulas are set up in a way where you should get the correct units with your variable. So mass should be in grams. Heat should be in some type of energy, which is going to be joules. C should be in energy divided by mass times temperature, which is going to be joules divided by grams degrees Celsius. And then temperature is going to be in degrees Celsius, or sometimes it's Kelvin, but that's not going to really matter depending on which one it is, because the math will be the same. So let me show you how I do this. In A, it says a 445 gram sample of ice at negative 58 degrees Celsius is heated until its temperature reaches negative 29 degrees Celsius. It says find the change in heat content of the system. The specific heat of ice is 2.05 joules divided by grams times degrees Celsius. So go ahead and underline all the numbers that you are given and label them. Are they a Q? Are they an M? Are they a C? Or are they a T? Okay, we're given 445 grams, that's a mass. Negative 58 degrees Celsius, that's a T. Negative 29 degrees Celsius, that's a T. And then the specific heat of ice, specific heat capacity, that is C. Our formula, we're going to write Q is equal to MC delta T, or we can also write Q is equal to MC, the final temperature, minus the initial temperature. Okay, we're going to plug in what we know. We know that we are solving for the change in heat, and that is Q. I always like to underline what I'm given, circle what I'm trying to find. So Q is not known. The mass that we are given is 445 grams. The specific heat that we're given is 2.05 joules divided by grams degrees Celsius. And then our delta T is our final temperature minus our initial temperature. Now, the way it's worded is going to make a big difference on which one is which. So the way we read this is that the sample of ice is at 58 degrees Celsius, and then it's heated until it reaches. So this is the initial, and this is the final. You got to make sure you use your context clues to make sure you correctly identify those. Because we are getting warmer, we know that Q should be positive because this should be an endothermic process. So we'll plug in negative 29 degrees Celsius minus negative 58 degrees Celsius. Now, depending on your calculator, plugging this in may be easy or difficult, but if you have the calculator that I always use, you can just plug it in just as it's written. If you don't, you may have to do this parentheses, then multiply it by this one, then multiply it by this one. Okay, so go ahead and let's solve these out. And our Q, I get 26455.25 joules. If we look back at our last step, we had all multiplication and we had two significant figures as our least amount of sig figs. So this will be 26,000 joules. Okay, so that's how we solve for Q. In B, we're going to solve for something besides Q. It says in going from negative 34 degrees Celsius to negative 3 degrees Celsius, a sample of ice absorbs 1.41 times 10 to the 5th joules. Find the mass of the sample. The specific heat of ice, again, is given as 2.05 joules divided by grams times degrees Celsius. Go ahead, underline all the numbers that you're given and label them, and then circle what we're trying to find. Our formula, we know, is Q is equal to MC delta T. Some people call this Q equals MCAT. Let's see what we can plug in. This time we do know for Q, and it's 1.41 times 10 to the 5th joules. Just because it's in scientific notation doesn't mean that we can't use it with scientific notation. M, we don't know, so I'm just going to plug in M. That's what it says, find the mass. C is 2.05 joules divided by grams times degrees Celsius. And then with our temperatures, we've got to make sure we read it carefully and we know which one is which. Well, Q is positive, so I know I got warmer. So my final temperature is negative 3 degrees Celsius, and then my initial temperature is negative 34 degrees Celsius. I'm going to get both of these solved out right away. And negative 3 minus negative 34 is 31 times 2.05 times M equals 1.41 times 10 to the 5th. 2.05 times 31, we get 63.55. M equals 1.41 times 10 to the 5th. Now we want to get M all by itself, so the algebra rules will tell us that M has a coefficient that's being multiplied by it, so to get rid of that, we will do the inverse and divide. So 1.41 times 10 to the 5th divided by 63.55. And M is going to be 2218.7254. And if you're paying attention to sig figs, our least amount of sig figs was 2 after we subtracted. So this will be 2200. And it's a mass, so the units of mass here are grams. Okay, now our very last, and this is the most difficult math probably of the entire semester. So we'll spend some time practicing in class, but you want to try to get this down right now. When we mix a hot substance with a cold substance, heat from the hot substance transfers to the cold substance until they reach thermal equilibrium. Okay, and that means that their temperature will eventually be the same. So, this is the same thing as saying the heat lost for my hot substance, and since hot things will lose heat to colder things, they'll have a negative Q. That will be positive Q for my cold substance. Okay, so go ahead and read question C, underline what you're given, circle what we need to find, and make sure you label whatever you're underlining as. Is it an M? Is it a T? What is it? Okay, our formula here is minus M hot, specific heat capacity of our hot substance, and our delta T of our hot substance equals M cold, C cold, delta T cold. And I'm going to rewrite this. This also is M hot, minus M hot, excuse me, C hot, TF or T final of my hot substance minus T initial, my hot substance, and that equals the mass of my cold substance, specific heat of my cold substance, and then T final of my cold substance minus T initial of my cold substance. And I'm very aware that this looks way complicated, but we just want to plug in what we know. First of all, when you read this, hopefully you notice that the hot substance here is aluminum, okay? And our cold substance is going to be water. So the mass of our hot substance, they tell us, is 175 grams. Because we know that the hot substance is aluminum, we can also plug in 0.900 joules divided by grams degrees Celsius for our specific heat of aluminum. We want to know the final temperature. We don't know that, okay? That's what we're trying to solve for. So T final is what we don't know. And then the initial temperature of our aluminum is 100 degrees Celsius. The mass of our cold substance, you may say they didn't give us the mass of our cold substance. What we really know is that the density of water, the density of H2O, is equal to 1 gram for 1 milliliter. So this is 40 grams of H2O. The specific heat capacity of water is 4.184 joules per gram degrees Celsius. And we're trying to solve for the final temperature of our water, and the initial temperature is 0 degrees Celsius. So, here's what's a little bit tricky. Do you notice that the final temperature is what we're solving for on both sides? That makes sense to me because we said at the beginning of this problem, heat from the hot substance will transfer to the cold substance until they eventually reach thermal equilibrium. So they will reach the same final temperature. Okay, give me a second. This is glitching. There we go. Sorry about that. Sometimes it just glitches on me. So let's solve this out. First of all, I don't like units. I want to solve for the final temperature. We know that that's in degrees Celsius. So I'm going to make this a little bit easier on my eyes. I'm going to change t final to x. For whatever reason, I feel a lot more comfortable with x as my variable. And then x minus 0 here, that's really just x. So hopefully that makes sense. So let us math these. We get negative 157.5. X minus 100 equals 40 times 4.184. That is 167.36 times x. This is going to be negative 157.5. X minus 100 equals 167.36x. Now, there's a couple steps that you can do here. Both are fine. You can distribute this. Okay, so I'm going to do it this way, and then I'm going to erase it and show you a second way that I actually like a little bit better. So let me actually just copy this before we get ahead of ourselves. So there's two ways to do this. Both ways are just as good. So we will distribute this. We get negative 157.5 x plus 15750 equals 167.36x. We will combine like terms, 157.5x. And we get 15750 equals 324.86x. We will divide to isolate our x in 324.86. And x actually ends up being 48.48 degrees Celsius. Okay. Now, another way that's just as good is to divide here. Divide by negative 157.5. So 167.36 divided by negative 157.5. We're going to get x minus 100 equals negative 1.0626x. We will combine like terms. So we get negative 2.0626x equals negative 100. We'll divide by negative 2.0626. Negative 2.0626. Negative 100 divided by negative 2.0626, and x equals 48.48. We know it's a temperature, so we know it should be in degrees Celsius. I tend to like this way a little bit better. This way is also good. So do what you are great at, okay? We don't need to reinvent the wheel when it comes to math. Do what you are consistently solving correctly.